torchnumel. Description: the torchnumel function calculates the total number of elements in a p-torch tensor. It essentially determines the size of the tensor by multiplying all the dimensions together. Inputs: tensor, the p-torch tensor for which you want to calculate the total number of elements. It can be of any data type and any dimension. Outputs: number of elements returns an integer representing the total number of elements in the input. Tensor. Steps: the function traverses all dimensions of the tensor. It multiplies the size of each dimension to obtain the total number of elements. Challenges and fixes. Challenge 1: no challenges. Challenge 2: no challenges. Torch set print options. Description: the torch set print options function is a utility in p-torch used to control the way tensors are displayed when printed. It allows you to customize how elements are formatted, how many elements are displayed, and other display-related options. Inputs: precision. This parameter determines the number of decimal places used when displaying floating point values. It accepts an integer value. Higher precision values lead to more digits after the decimal point. Line width. This parameter controls the maximum width of the output in characters. If the printed tensor exceeds this width, it will be wrapped to the next line. It accepts an integer value. Threshold. This parameter specifies the maximum number of elements that will be printed for a tensor. If the tensor has more elements than this threshold, only a summary will be displayed. It accepts an integer value. Edge items. This parameter controls how many elements at the beginning and end of a tensor will be displayed when the threshold is exceeded. It accepts an integer value. Schemode. This parameter enables or disables scientific notation for floating point values. It accepts a Boolean value. Setting it to true uses scientific notation. Float format. This parameter allows you to define a custom formatting string for floating point values. This string is used by the format function to format the float values. It accepts a string value. Use Unicode. This parameter determines whether Unicode characters will be used for special symbols, like ellipses and arrows. It accepts a Boolean value. Setting it to true enables Unicode characters. Maxcalls. This parameter controls the maximum number of columns to be displayed when printing a tensor. It accepts an integer value. Profile. This parameter is a string value that can be set to default, short, full, or long. This controls the level of detail in the tensor summary when the threshold is exceeded. Outputs: none. This function doesn't return any value. It directly modifies the global settings for tensor printing. Steps: the torch set print options function sets the global printing options for p-torch tensors. These options influence how tensors are displayed when you print them using the print function or when they are displayed in the debugger. Challenges and fixes. Challenge 1: truncated output. Sample use case that resulted in challenge 1: printing a large tensor with default options might display only a summary instead of the full tensor. Fixes to challenge 1: increase the threshold parameter to accommodate more elements. Set edge items to a higher value to display more elements at the beginning and end of the tensor. Challenge 2: inaccurate representation. Sample use case that resulted in challenge 2: displaying floating point numbers with insufficient precision might lead to inaccurate representation. Fixes to challenge 2: increase the precision parameter to display more decimal places. Challenge 3: unwanted scientific notation. Sample use case that resulted in challenge 3: scientific notation may not be desired when printing large values. Fixes to challenge 3: set the schemode parameter to false to disable scientific notation. Challenge 4 Limited column display. Sample use case that resulted in challenge 4. A wide tensor might be truncated, making it difficult to view all elements. Fixes to challenge 4. Increase the line width parameter to allow for a wider output. Challenge 5 Insufficient tensor information. Sample use case that resulted in challenge 5. Understanding the structure of a large tensor can be challenging without proper information. Fixes to challenge 5. Set the profile parameter to a higher value short, full, or long to display more information about the tensor in the summary. Torch set flush denormal. Description. The torch set flush denormal mode function in ptorch controls where the denormalized floating point numbers are flushed to 0 before they are used in computations. This behavior can affect the accuracy of calculations and potentially speed up computations. But it might introduce subtle changes in results. Inputs. Mode a Boolean value. True enables flushing denormals to 0, while false disables it. The default value is false. Outputs. None. The function does not return any value. It directly modifies the global setting for flushing denormals. Steps. The function sets the global flag in ptorch to determine whether denormalized numbers should be flushed to 0 during subsequent computations. When enabled, any denormalized floating point numbers encountered during computations will be automatically set to 0. Challenges and fixes. Challenge 1 Loss of precision. Flushing denormals to 0 can introduce subtle changes in the results of calculations, especially when dealing with very small numbers or numerical instability. Sample use case that resulted in challenge 1 performing calculations with extremely small numbers, close to the underflow threshold. Fixes to challenge 1. Carefully analyze the impact of flushing denormals on the accuracy of your computations. Consider using a different floating point format, such as bfloat16 or double precision, if precision is critical. If possible, restructure your calculations to avoid excessive reliance on very small numbers. Challenge 2 Potential performance degradation. In some cases, flushing denormals to 0 might not result in a significant performance improvement and could even lead to a slight slowdown due to the additional handling of denormals. Sample use case that resulted in challenge 2 working with datasets where denormals are not common. Fixes to challenge 2. Profile your code to measure the impact of flushing denormals on performance. Only enable flushing denormals if it consistently improves the performance of your code. Experiment with different combinations of data types and flushing modes to optimize for your specific use case. Torch, rand. Description. The torch, rand function is used to generate a tensor filled with random numbers from a uniform distribution on the interval 0, 1. This means that every value in the tensor will be a random number between 0 inclusive and 1 exclusive. Inputs. Size. This is a tuple of integers that defines the shape of the resulting tensor. For example, torch, rand2, 3 will generate a tensor with 2 rows and 3 columns. Out optional the output tensor. If provided, the generated random numbers will be stored in this tensor. D-type optional the desired data type of the returned tensor. If not specified, it will default to the default floating point data type of ptorch. Layout optional the desired memory layout of the returned tensor. Strided by default. Device optional the desired device for the returned tensor. Requires grad optional if set to true. The returned tensor will have its gradient tracked. Outputs. Tensor. A tensor filled with random numbers from a uniform distribution on the interval 0, 1. The shape of the tensor will match the provided size input. Steps. Determine the desired shape of the output tensor based on the size input. Allocate memory for the output tensor. Fill the allocated memory with random numbers from a uniform distribution between 0 and 1. Return the resulting tensor. Challenges and fixes. Challenge 1: incorrectly specifying the size input. This can lead to a tensor with an unexpected shape. Sample use case that resulted in challenge 1: torch. Rand 3 intended to create a tensor with 3 elements. However, a tensor with 3 rows and 1 column was created. Fixes to challenge 1: ensure that the size input is a tuple of integers that accurately represents the desired shape of the tensor. For example, use torch Rand 3 to generate a 1D tensor with 3 elements. Torch Rand 2 3 for a 2D tensor with 2 rows and 3 columns. And so on. Challenge 2: not specifying the correct data type for the tensor. This can lead to unexpected behavior or errors if the data type is not compatible with subsequent operations. Sample use case that resulted in challenge 2: torch Rand 2 3 dtype torch.int intended to create a tensor of integers. However, an error is thrown because the default dtype of torch Rand is float. Fixes to challenge 2: use the dtype argument to specify the desired data type for the tensor. For example, torch Rand 2 3 dtype torch float for a float tensor. Torch Rand 2 3 dtype torch.int for an integer tensor. Or torch Rand 2 3 dtype torch bool for a Boolean tensor. Challenge 3: using torch Rand in a loop to generate a large number of random numbers. This can be inefficient in terms of memory and processing time, especially if the random numbers are not needed all at once. Sample use case that resulted in challenge 3: for I in range 1000 a torch Rand 1000 intended to generate 1000 tensors each with 1000 random numbers. Fixes to challenge 3: consider using torch RANDN to generate random numbers from a standard normal distribution instead of a uniform distribution, as this can be more computationally efficient for generating a large number of random numbers. Alternatively, use torch RANDINT to generate random integers from a specific range. Torch RAND-like. Description: the torch RAND-like function generates a tensor filled with random numbers from a uniform distribution between 0 and 1 with the same size and data type as the input tensor. Inputs. Input 1: input tensor. The input tensor whose shape and data type will be used to create the output tensor. Outputs. Output 1: output tensor, a new tensor filled with random numbers from a uniform distribution, having the same size and data type as the input tensor. Steps. Step 1: the function determines the size and data type of the input tensor. Step 2: it creates a new tensor of the same size and data type, filling it with random numbers from a uniform distribution. Challenges and fixes. Challenge 1: the input tensor should be a valid p-torch tensor. Sample use case that resulted in challenge 1: providing a non-tensor object as input. Fixes to challenge 1: ensure the input is a valid p-torch tensor. Challenge 2: the input tensor should have a defined shape. Sample use case that resulted in challenge 2: providing a tensor with an undefined shape. Fixes to challenge 2: ensure the input tensor has a defined shape. Challenge 3: the output tensor might not be contiguous in memory. Sample use case that resulted in challenge 3: performing operations on the output tensor that require contiguous memory. Fixes to challenge 3: use output contiguous to ensure the output tensor is contiguous in memory. Challenge 4. The output tensor might have a different data type than the input tensor. Sample use case that resulted in challenge 4. Specifying a different data type for the output tensor than the input tensor. Fixes to challenge 4. Ensure the desired data type is specified for the output tensor using the D-type argument. Torch. RANDN. Description. The torch, RANDN function generates a tensor filled with random numbers from a standard normal distribution mean 0, std1. It utilizes the Box-Muller transform to achieve high-quality random numbers. Inputs. Size a tuple specifying the shape of the resulting tensor. The dimensions can be integers or lists. If not provided, the function generates a single random number, a tensor of size 1. Outputs. Tensor, a tensor of the specified size, containing randomly drawn numbers from a standard normal distribution. Steps. Initialization. The function initializes a tensor of the specified size. Random number generation. It populates the tensor with random numbers generated from the standard normal distribution. Challenges and fixes. Challenge 1. Understanding the distribution. Sample use case trying to generate numbers from a different distribution. Fixes. Scaling and shifting. Use torch, RANDN to generate the base random numbers. Then apply scaling and shifting to achieve the desired mean and standard deviation. For example, torch, RANDN size std mean generates a tensor with a mean of mean and a standard deviation of std. Other distributions explore other p-torch functions for generating numbers from different distributions, such as torch, rand uniform distribution, or torch, randint discrete uniform distribution. Challenge 2. Controlling the seed. Sample use case generating the same random numbers across multiple runs. Fixes. Torch, manual seed. Use torch, manual seed to set a specific seed for the random number generator. This ensures that the same sequence of random numbers is generated whenever the seed is the same. Torch, generator. For more control, use the torch, generator class to create a custom generator object. This allows you to set specific seeds and control the randomness process at a finer level. Torch, RANDN like. Description. Inputs. Input a tensor, which acts as a template for the output tensor. This means the output tensor will have the same shape, data type, and device as the input tensor. Output a tensor filled with random numbers from a normal distribution with a mean of 0 and a standard deviation of 1. Steps. Step 1. The function takes an input tensor. Step 2. It generates a tensor with the same shape, data type, and device as the input tensor. Step 3. It fills the output tensor with random numbers drawn from a standard normal distribution. Mean 0. Standard deviation 1. Challenge 1. Misunderstanding the input argument. The function requires a tensor as input, not a scalar or other data type. Sample use case that resulted in challenge 1. Calling torch, RANDN like 5 would raise an error because 5 is not a tensor. Fixes to challenge 1. Ensure the input argument is a valid tensor. Challenge 2. Unexpected shape or data type of the output tensor. The output tensor will have the same shape and data type as the input tensor, which might not be the desired outcome. Sample use case that resulted in challenge 2. If the input tensor is of type torch.int64, the output tensor will also be of type torch.int64. Fixes to challenge 2. Cast the input tensor to the desired data type before calling torch, RANDN like. If you need a specific shape, consider creating a new tensor with the desired shape and then using torch, RANDN like with that. Tensor. Torch, randint. Description. The torch, randint function generates random integers within a specified range. Inputs. The lower bound of the range inclusive. It can be a scalar or a tensor. If a tensor, it must be a one-dimensional tensor of the same size as size. High. The upper bound of the range exclusive. It can be a scalar or a tensor. If a tensor, it must be a one-dimensional tensor of the same size as size. Size. A sequence of integers defining the shape of the output tensor. It can also be a single integer to generate a one-dimensional tensor. Generator optional. A random number generator rung. D-type optional. The desired data type of the returned tensor. Defaults to torch.int64 if not specified. Layout optional. The desired layout of the returned tensor. Defaults to torch, strided if not specified. Device optional. The desired device of the returned tensor. Defaults to the current device if not specified. Outputs. Output a tensor of random integers with the specified size. D-type, layout, and device. Each element of the tensor will be a random integer in the range low. High. Steps. The function first checks the input arguments for validity. It ensures that low is less than high, that the size argument is valid, and that the other optional arguments are valid. The function then generates random integers within the specified range using the provided generator or the default generator if none is specified. Finally, the function returns a tensor containing the generated random integers with the specified size. D-type, layout, and device. Challenges and fixes. Challenge 1. The input arguments are invalid. Sample use case that resulted in challenge 1. The low value is greater than or equal to the high value. Fixes to challenge 1 ensure that the low value is strictly less than the high value. Challenge 2. The size argument is invalid. Sample use case that resulted in challenge 2. The size argument is not a sequence of integers or a single integer. Fixes to challenge 2 ensure that the size argument is a valid sequence of integers or a single integer. Challenge 3. The generator argument is invalid. Sample use case that resulted in challenge 3. The generator argument is not a valid random number generator. Fixes to challenge 3 ensure that the generator argument is a valid random number generator. Challenge 4. The D-type argument is invalid. Sample use case that resulted in challenge 4. The D-type argument is not a valid data type. Fixes to challenge 4 ensure that the D-type argument is a valid data type. Challenge 5. The layout argument is invalid. Sample use case that resulted in challenge 5. The layout argument is not a valid layout. Fixes to challenge 5 ensure that the layout argument is a valid layout. Challenge 6. The device argument is invalid. Sample use case that resulted in challenge 6. The device argument is not a valid device. Fixes to challenge 6 ensure that the device argument is a valid device. Torch, randint-like. Description. Inputs. Input the tensor whose size and D-type will be used to create the output tensor. Low optional. The lower bound for the random integers to be generated inclusive. If not specified, defaults to 0. High. The upper bound for the random integers to be generated exclusive. D-type optional. The desired data type of the returned tensor. Defaults to the D-type of the input tensor. Layout optional. The desired layout of the returned tensor. Defaults to the layout of the input tensor. Device optional. The desired device of the returned tensor. Defaults to the device of the input tensor. Pin memory optional. If set to true, the returned tensor will be pinned to memory. Defaults to false. Requires grad optional if set to true. The returned tensor will have requires grad set to true. Defaults to false. Generator optional. A torch generator object to use for drawing random numbers. If not specified, a global default generator will be used. Output a tensor filled with random integers with the same size and d-type as the input tensor. The elements of the output tensor will be in the range low, high. Steps. The function first determines the size and d-type of the output tensor based on the input tensor. It then generates random integers within the specified range low, high using the provided generator or the default generator. Finally, the generated random integers are populated into the output tensor. Challenge 1 out of bounds error if the specified high value is lower than the low value. The function will raise a value error. Sample use case torch, randint like torch, tensor 1, 2, 3, high 0, low 1. Fixes to challenge 1 ensure that high is greater than low. Challenge 2 incorrect data type if the specified d-type is not compatible with integer values. The function will raise a type error. Sample use case torch, randint like torch, tensor 1.0, 2.0, 3.0, d-type torch, float 32, high 5. Fixes to challenge 2 ensure that d-type is compatible with integer values. Challenge 3 incorrect device if the specified device is not supported by the current system. The function will raise a runtime error. Sample use case torch, randint like torch, tensor 1, 2, 3, device CUDA, high 5 when there is no CUDA device available. Fixes to challenge 3 ensure that the specified device is available and supported. Torch, randperm. Description. The torch, randperm function generates a 1D tensor of random permutation of integers from 0 to n1, where n is the input argument. The function is often used to shuffle data for tasks like training machine learning models. Inputs. N. This is an integer representing the number of elements in the permutation. The returned tensor will be of size n. Outputs. Output a 1D tensor of integers ranging from 0 to n1. In a random permutation, the shape of the output is n. Steps. The function internally generates a random permutation of integers from 0 to n1. The generated permutation is then returned as a 1D tensor. Challenges and fixes. Challenge 1 incorrect input type. The input argument n must be an integer. Providing a non-integer value will result in a type error. Sample use case torch, randperm ABC. Fixes ensure the input argument n is an integer. Challenge 2 negative input. The input argument n must be a non-negative integer. Providing a negative value will result in a value error. Sample use case torch, randperm -5. Fixes ensure the input argument n is a non-negative integer. Challenge 3 0 input. The input argument n must be a positive integer. Providing a 0 value will result in an empty tensor. Sample use case torch, randperm 0. Fixes ensure the input argument n is a positive integer. Torch, empty. Description. Torch, empty is a function in ptorch that creates an uninitialized tensor of the specified size. It allocates memory for the tensor but does not initialize its values. This can be useful for situations where you need to create a tensor quickly and then fill it with data later. Inputs. Size a tuple or list specifying the desired shape of the tensor. For example, 2, 3 would create a tensor with 2 rows and 3 columns. D-type an optional argument specifying the data type of the tensor. Defaults to torch, float 32. Other valid data types include torch.int32, torch, bool, etc. Layout, an optional argument specifying the memory layout of the tensor. Defaults to torch, strided. Other valid layouts include torch, sparse and torch, sparsexer. Device, an optional argument specifying the device where the tensor will be stored. Defaults to the current device. You can use torch, device CPU, or torch, device CUDA to specify the device. Requires grad, an optional argument specifying whether the tensor should track gradients. Defaults to false. Outputs. Tensor, an uninitialized tensor with the specified size. Data type, layout, and device. Steps. The function allocates memory for the specified tensor size. The allocated memory is not initialized with any specific values. Challenges and fixes. Challenge 1, an initialized tensor values. Since the tensor is not initialized, it will contain garbage values. This can be problematic if you attempt to use the tensor without first assigning values to it. Sample use case that resulted in challenge 1: using torch, empty to create a tensor and then trying to perform calculations with it without first filling it with values. Fixes to challenge 1: fill the tensor with appropriate values before using it for calculations. You can use methods like torch, randn, to generate random values. Torch wants to create a tensor filled with ones, or assign values directly to the tensor. Challenge 2: incorrect data type. If you do not specify the dtype argument, the tensor will default to torch, float 32. This may not be the desired data type for your application. For example, if you need to store integers, you should explicitly specify dtype torch.int32. Sample use case that resulted in challenge 2: creating a tensor to store integer values but not specifying the dtype argument. Fixes to challenge 2: specify the desired data type using the dtype argument. For example, dtype torch.int32, dtype torch, float 64, dtype torch, bool, etc. Challenge 3: incorrect device. If you do not specify the device argument, the tensor will be created on the current device. This may not be the desired device for your application. For example, if you need to store the tensor on the GPU, you should explicitly specify device torch, device CUDA. Sample use case that resulted in challenge 3: creating a tensor and expecting it to be stored on the GPU without specifying the device argument. Fixes to challenge 3: specify the desired device using the device argument. For example, device torch, device CUDA, device torch, device CPU, etc. Torch tensor. Description: a fundamental data structure in PTorch, representing a multi-dimensional array that can store numerical data of various types. Tensors are essential for performing numerical computations and deep learning operations. Inputs: data. The numerical values that form the elements of the tensor can be integers, floats, or other numerical data types. Shape: the dimensions of the tensor, defining the number of elements along each axis. Data type: the type of data stored in the tensor, e.g. float 32, int 64. Outputs: tensor object. The PTorch tensor object containing the provided data, shape, and data type. Computed results: tensors can be used in various mathematical operations, addition, multiplication, etc. Returning new tensors with the computed results. Steps: creation: tensors can be created using various methods like torch, tensor, torch, array, torch, zeros, etc. Operations: tensors support various operations like element-wise arithmetic, matrix multiplication, indexing, reshaping, etc. Manipulation: tensors can be manipulated by changing their shape. Data type: or values. Computation tensors are used to perform numerical computations like linear algebra, convolutions, and other deep learning operations. Challenges and fixes. Shape mismatch, trying to perform operations on tensors with incompatible shapes. Sample use case that resulted in challenge 1, adding two tensors with different numbers of elements. Fixes to challenge 1, reshape one of the tensors to match the other's shape or use broadcasting rules if applicable to automatically expand the smaller tensor. Data type mismatch, trying to perform operations on tensors with different data types. Sample use case that resulted in challenge 2, performing arithmetic on a float tensor and an integer tensor. Fixes to challenge 2, cast both tensors to the same data type before performing the operation. Memory management, dealing with large tensors and ensuring efficient memory usage. Sample use case that resulted in challenge 3, creating a massive tensor that exceeds available memory. Fixes to challenge 3 utilize techniques like data loading in batches, GPU memory allocation, or tensor storage on disk to manage memory effectively. Device placement, ensuring tensors are allocated on the appropriate device CPU or GPU for optimal performance. Sample use case that resulted in challenge 4, performing computations on a GPU without transferring the tensor to the GPU. Fixes to challenge 4, use tensor to device to move the tensor to the desired device.